what do I do with this science and how do I make it useful for somebody. We are the third largest startup ecosystem in the world today, and for chemical engineers, it's a great opportunity. Honestly, I did not even know about UDCT. It was a friend who told me
It
that.
still is one of the country's best kept secrets. Namaskar and welcome to another edition of the Professor Mahesh Podcast, your resource to help you make informed career decisions. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement at IITM. IITM Global is a platform to take everything IIT Madras and everything India to the global stage. Our teaching, our research, our entrepreneurship, our our process of planning and other aspects of India and IIT Madras. I'm grateful to them for supporting this podcast. Today's edition will feature one of India's foremost chemical engineers, a thought leader behind many of India's missions, the current director of the National Chemical Laboratory in Pune, Professor Ashish Lele. Ashish, thank you very much for making time in your busy schedule to come be part of this conversation. It's a delight. Let's start with a little bit of your own journey through chemical engineering. You studied at UDCT, which is one of India's premier chemical engineering schools. Let's help me understand your career journey from there.
Sure, Mahesh, thank you so much, first of all, for inviting me to this wonderful platform. And when you called me and asked me about it, I thought I wish I had such a platform available to me when I was a student and trying to make a decision on what career I want to follow. We didn't have that kind of resource at that point of time. So I think I envy to some extent the young students right now who are making career choices and have access to such kind of conversations. So I started my chemical engineering journey at UDCT. I did my graduation from UDCT in 1988 and then went to the University of Delaware in the US to get my PhD. I completed that in 1993. I had always wanted to come back for some reason, which are more personal than anything else. So right after my PhD, within a month, I was back in India. And I was fortunate to get an employment in NCL, National Chemical Laboratory. So I joined right away. I've been there for a very long time now, with a small break in between, but I've been at NCL for a very long time. So I'll tell you a little bit about my journey in NCL. I've sort of break that into maybe 4 segments. The first 12 years was I was a young chemical engineer just starting my career at NCL, and I was encouraged to pursue a lot of more sort of basic sciences, right? A little more academic in orientation. I must tell you before that NCL is a unique place, I would say, where you have a good blend of not just doing science but also translating it into technologies which could make a difference, right? So there's always this right from beginning at NCL, this thought process of doing science and applying it. And in fact, the motto of the lab, as it is enshrined in our main building foyer, says that the purpose of this laboratory is to advance knowledge and to apply chemical sciences for the good of the people. It's a very simple statement, but I think it's very profound. And over our last 75 years of journey, we have never had a single thought of changing that motto, the purpose of the laboratory. So as you can see, it's advancing knowledge, which is doing science, and also applying it with the bigger goal of, for the good of the people or the country as such. So when you start a career at NCL, I was told to focus a little bit on the first part, which is advancing knowledge, right? And establish yourself as a chemical engineer, get in the thick of things. But there was always a reminder that you should constantly think at the back of your mind of what do I do with this science? I'm developing this science, but why am I doing it? How do I apply it? And how do I make it useful for somebody, right? So there was always that thinking at the back of the mind, because that's the that's the gene, that is the DNA of NCL. So I started working in polymer science, which has been my sort of core expertise at that point of time. My PhD was in polymers, although a chemical engineer, but the major was in polymer science. And I started working in NCL on polymer science. I did a lot of thermodynamics of soft materials, rheological studies, fluid dynamics of viscoelastic complex materials. Right. So that was a lot of basic research. But at the same time, I had started working with industry, and industry which are interested in soft materials in general, which is a class of materials that involves plastics, polymers as we call it. It involves a lot of personal care products, for instance, food products. There's a whole lot of materials that come under the category of soft materials, right? As the word means, it is softer than metals and wood and things like that. So one of the key things there, which I think was very fundamental to material science, is the structure property performance relations, as we call it, right? So how does the structure at various hierarchical levels, from atomistic to macro scale, the hierarchy of structures in materials, how does that control the properties of the materials? Those properties, they translate into performance of the materials, right? And those performance translate into marketplace, right? So there's a link between all of this, and if you understand that link, then the science gets related to the marketplace in that sense, right? And that was the thinking behind my association with industries who are interested in these areas. So I was working with both multinational companies and Indian companies working in the plastics area, because that polymers was my basic background, right? And we're looking at commodity polymers like polyethylenes and polypropylenes, and how does the molecular structure of these materials translate into their flow properties, their crystallization behavior, their solid state properties, and how does all of that translate into actual performance of a product, right? And I think that connection between what we do in basic sciences and what the industry can derive out of that knowledge stayed with me throughout my career, because what I was doing, I could see was of great interest to the industry. So while at the same time I was publishing papers, I was also working with industry to apply that science into problems that would be of interest to them. So I could see the sense of the NCL's DNA in what I was doing, and that was very useful to me. It was very exciting. So that was for the first 12 years. At some point of time, I said enough of polymers. There are bigger problems that need to be solved. And again, the reason why I sort of started thinking about it was, in NCL you get this opportunity to listen to a lot of research happening within the chemistry, materials, chemical engineering domain, happening across the lab. You're invited to attend meetings where some large ideas are being discussed, and road mapping of what needs to be done in the next 10 years is discussed. So sort of get involved in that, and you feel you get exposed to what might be bigger problems that are crying for solutions. And of course nobody forces you to say stop what you're doing and work in this now. It's up to you. If you feel like maybe I should do something in this area, you're invited to. And that happened to me in about 2005. I happened to be in a meeting where there was a discussion on would hydrogen economy evolve in this country, would hydrogen become a clean energy vector that may be important to the country. And this was back in 2004-5. So you can imagine that it was 15 years, 10-15 years before the country really realized that hydrogen is an important fuel. So up early, we had this thinking, this brainstorming, and that brainstorming resulted into a larger program. And I felt that maybe this is an area that I should now start looking into, right? So for the next 12 years, I sort of got involved into these programs where completely switched from polymers to clean energy with hydrogen as a focus, and started looking at one of the technologies in the hydrogen value chain, which is fuel cells, which is using hydrogen to produce clean electricity, right? And this idea was, can we develop that technology indigenously, completely within India? Is there anything in this technology that we can't do? Maybe we should be ready with this technology package if and when hydrogen really arrives on the scene and industry starts looking for hydrogen technologies. Maybe we should be ready for it, right? So sort of developing fuel cell technology ground up from absolute scratch to large scale application of fuel cells was that journey in that 10, 12 years that I had a great privilege to be part of that journey, right? We literally started from scratch. We built brick by brick. And today I can very proudly say that we can build large fuel cells. We deployed them in many applications. We've licensed the technology. And today, India is looking for those kinds of technologies. So I think it was a very wonderful journey for me. It also taught me many things beyond science and beyond technology. How do you converse with industry? How do you foresee the future? What are the risks involved? How do you mitigate those risks? There are technology risks, there are financial risks, there are market risks. How do you get around these problems, right? And how painful is it to continue on a technology development journey for 12 years? It's not easy. It's a very difficult job. So all of those experiences, I think, was a fantastic learning experience for me. At about 2016-17, I was thinking that, how I have worked with industry quite a bit. For nearly 15, 17 years, I've worked with industry. But it has always been that the industry comes to me saying, here is a good problem statement. Can we do something together on this, right? Of course, that problem statement has evolved by discussions with us, but I realized that there's a lot of work that they do in the background to arrive at a problem statement, right? And much of that is not out in the open domain, right? It's very strategic to the industry, but I knew that they do a lot of work there, right? And I wanted to experience what is it, because that was a missing part for me. In my learnings, that bit was, I think, missing. So I thought I should make another jump and move out of NCL and join a private sector to sort of learn how is it done there. I had an opportunity to work with India's largest private sector company, Reliance Industries. I was also very fortunate that I worked with leadership there, and very fortunate that my learnings and experience in the hydrogen technology development was useful to the company. Because in my 3 years in Reliance, I was involved with a very core strategic group that evolved the first roadmap for hydrogen business for Reliance. And I think it was one of the most exhilarating experience for me. How people from extremely diverse backgrounds within a company suddenly come together. It's almost like a self-assembly process. They all realize that Reliance wants to get into this in a big way, and I want to be part of that journey, right? And so people self-assemble. It was quite a bit of learning experience for me, right? And from what was a 3 or 4 man team, of which I was sort of a leader, it became within no time a 55, 60 man group. And I didn't call anybody. People called me and said, I hear you're doing something in this area. You're creating some strategic roadmap for a company. We would like to be part of it, and we would like to contribute in this way. So it was great, and then it was all during COVID period, and I learned phenomenal things from it. Huge learning in techno-economics. To details to which the companies go in assessing technologies from a technological, technical, scientific point of view, as well as from a financial and market point of view, right? Uh, and that was the bit that I didn't have access to when I was at NCL. It was a huge learning experience for me. Uh, and I think with that learning, of course, I came back to NCL. The reasons for that are something else, but when I came back to NCL, I think that learning has stayed with me. As the director of the institute, this is my last leg of my professional career now at NCL as a director. I can now bring in all of these components together. At least that is what I think, that I can now identify the problems, the areas, the themes, both which are required today and maybe 10 years from now, right? And how do I make those assessments? Should I get into this domain at all or not, right? What are the factors that determine that decision making, right? It's internal factors, external factors, right? I think that learning both at NCL and at Reliance to me has been very important as a director of the laboratory, to decide what NCL should be doing now and in the future. So at NCL now we are looking at very core domains where some of them are businesses today for NCL and some of them are likely to be business for NCL 10 years from now. Just as we started in hydrogen 10 years before the market really picked up, what should I do in NCL now so that 10 years later NCL will be at the right place when the country is at the right place, so I think all of this journey has been a great learning experience for me. That's roughly.
And it all started at UDCT. I want to go back to that. You would have been surrounded by some of India's most brilliant people there. I had a very brief interaction with Professor M.M. Sharma, Dr. Mashelkar, people like that. What was it like being a student at UDCT, surrounded by these stalwarts that were building a fledgling chemical engineering industry in India?
I think I've been extremely lucky as a chemical engineer to be at that institute. My formative years as a chemical engineer in UDCT have been a turning point in my life, honestly. As a graduate of 12th exams, in those days, it was not the internet days, right? It was not the mobile phone days. So information was not available very easily, right? Exposure to various fields, career fields, was not very easily available. You would talk to people and understand from them about what this career, maybe in mechanical engineering, would mean, or chemical engineering would mean, or a doctor would mean. You talk to people and get information. Nothing was available easily, right? So just after the 12th exam, honestly, I did not even know about UDCT. It was a friend who told me
It
that.
still is one of the country's best kept secrets.
I would imagine so. In Mumbai, where I was growing up, VJTI was the college for mechanical engineering, right? And I wanted to be an engineer. My father was a civil engineer, and VJTI was like the college to go to, or one of the best engineering colleges to go to. So my eyesight was on VJTI. So group of us, friends went, and we used to have, we had to fill forms, application forms for seeking admission into colleges, right? And you would go around various colleges, get their admission forms, fill them, and then submit them, and then wait for a list, an admission list, right? And see if your name comes on that list. So that was the time. So I went to visit I filled out the form, and then one of my friends told me that there is a college right in front of VJTI. And there's a college right in front of VJTI, which also is a good engineering college, but it teaches chemical engineering. since we are filling up many forms, why not fill that form also, right? And I looked at that college in opposite VGTI. I thought the building looked pretty nice, old sandstone building. It had a nice feel about it. So we went, filled the forms, and submitted, and lo and behold, I got my name appeared in the first list of admissions, right? By then, however, I had started asking about what is chemical engineering and why should I pursue that career, right? My father told me that I know nothing about chemical engineering, so I can't help you, right? But there was an IIT graduate in the place where I lived in Mumbai. There was one of my friends, a senior guy, was at IIT Bombay pursuing chemical engineering, and I asked him, and he said that uh, if you get admission to UDCT, forget anything else. He said at that time he said forget even IIT Bombay and just go for UDCT, right? Uh, Trust was an important factor in our lives, right? So I trusted him, and without too much of thinking, I don't overthink. That's that's just my thinking. So I said, if he's telling me something like this, and he's my senior, and he's advising me this, maybe I should just do it. How do I know what is mechanical engineering anyway, or civil engineering? I don't know anything about them. So is true with chemical engineering. So I accepted it. I also lived in an area where, in Mumbai, there are a lot of chemical industries around in the outskirts of Mumbai. I used to live in Navi Mumbai, which used to have a whole belt of chemical industries. So seeing chemical plants was a daily thing for me. So it was not unfamiliar. But not that I understood anything about it, but I just saw them, right? And so I entered UDCT. I remember the first day, first lecture of all our fresh, entrants was by Professor M.M. Sharma. And for 1.5 hours, he talked about what chemical engineering was and what is the impact of chemical engineering to the society, to the country, to the world, and it was one of the most fascinating lectures that I ever heard. I mean, coming from M.M. Sharma, you can imagine the doyen of chemical engineering in this country. But what a fortunate day that was for young students like us who have known nothing about this area, and the best man in the country comes and tells you what this field is all about. And that one lecture was enough to tell me that I think I'm in the right place. And so I think that 4 years journey was great. We had some of the best chemical engineers in the country. M.M. Sharma, J.B. Joshi, Rajadhyaksha, Chandalia, Tiwari. I mean, they were absolutely fantastic people. The phenomenal thing about UDCT, which is today ICT, by the way, so UDCT was that the connect with industry was so strong right from the beginning. We used to have our BTech problem statements coming from industry. It was an industry originated problem. Every student would have to do a BTech project in the final year, which was an industry focused problem. It was not something that a professor thought about. It was what the industry told them to do. Our BTech, exams, oral exams would be conducted by industry. We had to do internships with industry, compulsory, right? So this connect with industry was so phenomenal. We used to see all these people in UDCT all the time. The CEOs and the managing directors or the CTOs of companies sort of were there in UDCT all the time, right? So how an academia should be deeply connected with industry was to us ingrained right from the beginning. In fact, I did not know that there was anything else other than that. So all this talk today about industry, academia, collaborations and all, I find it a little strange, because isn't that how it should be? that has been my feeling, but I realize now that was because of UDCT as a place, and that is what the environment there was. So I think it was a fantastic experience to be there.
Wonderful. I think Uh, there are pockets of excellence like UDCT, like ICT, all over the country that I wish we all sort of brought out a little more consciously. So let's switch topics a little and talk about what is chemical engineering. I spent yesterday a little consciously thinking about this, living the day. And I realized at the end that I started with a little toothpaste on my brush and ended my day with a sip of water from my RO filter. And throughout, when I reflect, the amount of chemical engineering that I was exposed to living my day is phenomenal. I don't think we realize that. Let's talk a little bit about the breadth of chemical engineering. What are all the topics that this field covers? And we'll move on from there.
So, normally I think the misconception about chemical engineering is that it is all about chemistry, right? And of course, it is a lot about chemistry, right? But there is so much more to it, right? Today, for example, there is a whole lot of biology. A huge number of chemical engineers today work specifically in systems biology or biomanufacturing, fermentation, chromatography, gene editing. You have chemical engineering practically everywhere in biology. In fact, the Nobel laureate in evolutionary biology is a chemical engineer, right? So think of AIML, for instance. I think one of the big things required in AIML is data, is access to data, right? If you don't have good quality data and a huge amount of data, you can't do much about it. Right? In chemical plants, good chemical plants, data has never been a problem because chemical plants have sensors all over the place. Right? There is a DCS system, a SCADA, a DCS, where data is mined. Gigabytes of data exists real time being generated in plants on a minute by minute, second, daily basis, right? So, for an AI/ML expert to apply those tools to chemical plants is actually relatively easy because data is available.
Good quality data.
Excellent quality data is available and historical data is available, right? Over decades of data can be available. Think of, as I said, soft materials. As you rightly said, toothpaste. Think of plastics. Think of granular materials, right? All of these require one to understand the physics behind it, but also the fluid dynamics of it. I know you understand fluid dynamics more than anybody else, and you need to understand how these materials flow. You need to understand how the structure in these materials evolve, because ultimately that is what tells you whether this toothpaste is better than that or this paint is better than that. So a huge amount of the basics of chemical engineering exist in these materials. So I think chemical engineering has been, I think that one of the strengths of chemical engineering is the fundamentals can be applied in any of these fields, right? And what are those fundamentals? The fundamentals has to be the basic physics, chemistry, biology, because you need to understand that foundation, right? And then you go to one level up and say, how does energy flow? How does mass flow? How is energy conserved? How is mass conserved in a given system? That system could be a chemical plant. It could be a product. Manufacturing of that product, for example, or as the product performs in an environment, you need to understand heat and mass balance in these. So that's the core of chemical engineering: understanding energy conservation, mass conservation, momentum conservations, right? So what we call transport phenomena, right? So you have the basic fundamentals of the core science, the physics, chemistry, biology, today maybe data science, right? And then a level up and saying all the transport phenomena, the thermodynamics that is associated with it. And of course, chemistry, right? Chemistry is a very critical part of it. So the fundamentals of chemistry, the reactions that happen, the rates of reactions, So all of those and much more comprises chemical engineering today. Yeah. And that is why chemical engineers, you will find them not only in chemical industry, but you will find them in Unilever and Godrej, who are making personal care products and agrochemicals, and you will find them in steel industry. A lot of chemical engineers are hired to run steel plants, design steel plants, cement industry, fertilizer industry.
Quite counterintuitively, I found a large number in places like Intel and IBM because fabrication, semiconductor fabrication, is a chemical engineering process.
So these are all chemical material processes. Ultimately, when you manufacture something, you need some energy input, you need some material inputs, raw materials have to go in to bring a product out, energy has to come in to convert raw materials into a product. So you are always talking about heat flows and mass flows and reactions happening, and all of that put together is chemical engineering.
So it is not an understatement to say that there is no industry that will not need chemical engineers.
Absolutely, I fully agree with you on that.
Second point I'm picking up from what you're saying, it also seems to be one of the sort of few or only engineering disciplines that borrows in some good measure from mathematics, physics, chemistry, and biology. As you said, there is a significant bio footprint within chemical engineering. Let's talk a little bit about how young people think about their careers. Clearly, chemical engineering is one of those disciplines that cuts across multiple sectors, multiple segments. Take FMCG, food, industrial chemicals, environment. We'll probably come back and talk about environmental engineering as well. In your interactions with early career professionals, say at NCL or other places, what are some common questions you encounter? We talked of one question that says chemistry, while chemical engineering borrows from chemistry, chemical engineering is not chemistry, right? There is also seems to be a misconception that chemical engineering is a very dirty profession, right? You talked about how AI is actually perfect for chemical engineering than probably any other engineering profession. What are some other similar questions that you may have encountered from young professionals?
Yeah, so one set of questions is about, what is it uh, as a career to me? What does chemical engineering offer me as a career? If I become a chemical engineer, what are the various options that I have to make my career, to build my career, right? And the other set of questions is, should I choose chemical engineering as a career over some other options that are available to me? So generally, I think young students are bothered about these two aspects, right? So the first aspect is, what is chemical engineering, which we talked about. They often come with this misconception that I will have to work in very dirty and unsafe chemical plants. And of course, they read about, accidents that happen in chemical plants, and uh, those of them who live around the chemical industry belt would sometimes smell chemicals, right? And so their conception, I don't say that it is entirely wrong, but they feel that being a chemical engineer would force them to work in such kind of dirty and unsafe environments. Okay, uh, but that is not really the reality, right? You go to a refinery today, any of the refineries in the country today, and if you were to roam around the plant, you will not see any people there. It's entirely an automated plant. You will absolutely not see a single soul in the plant. Millions of tons of fluid is moving around in the plant, materials are getting formed, steam is flowing around, gases are flowing around, huge reactors, huge columns where separations are happening, but not a single soul in the plant. The entire plant is automated, is digitalized. and you'll see people sitting in nice, comfortable, air-conditioned rooms, looking at big screens, and seeing the data from the plant, real-time data from the plant on these big screens, and they're looking at, everything is fine, working fine, So what people think today of, I may have to go and turn a valve and stay in hot and dirty places is really not the case today, right? And so that's one of the misconceptions. Do I have to work as a chemical engineer in these dirty and unsafe plants? The second misconception is that this field is stagnated. You know, that chemical engineering is stagnant, is not moving around, but the more glamorous, financial services, IT, which are more glamorous service-oriented careers, there's a lot of things happening there, right? Because I think the social media is always abuzz with finance, with IT. Not much comes from chemical engineers. It does, but not in the kind of media that a common man would.
It's not packaged for that group.
That's right, right? So young people might feel that chemical engineering is a very sort of stagnated career. But again, that is a complete misconception, right? I think as, some of the world's toughest problems today, right, whether it is climate change, whether it is all kinds of pollution, air, water, solid, land pollution, it's the chemical engineers who are rightly trained, have the right knowledge and the right mindset to be able to solve these problems, right? And therefore, chemical engineering is moving in all kinds of directions today, right? So it is absolutely not a stagnant field. It's a career that is growing in all kinds of directions. Like you said, semiconductors. You cannot set up a semiconductor chip making plant or a silicon wafer manufacturing plant without chemical engineers. It's impossible to do it, right? So again, that's a misconception. It's not a stagnant field. It's growing in all these directions. The third issue is about how do I make this career choice? What is it that a chemical engineering profession offers me as a young graduate versus, again, I'll come back to IT and financial services, what does that offer me? And I think that is a problem today, right? The service sector is much more glamorous today than chemical engineering. It's a little unfortunate, but that is how it is. The pay packages are so asymmetric. The pay package in a financial sector or an IT sector are so much more than what a manufacturing sector offers you, right? And that is a reality. And, you and I can't change that very much. But it does affect young people who make their career choice. And so often I see and I hear that young people who get into chemical engineering department are there because they have not got admitted into a computer science department. So their first choice is computer science, maybe third, fourth choice is chemical engineering. They start their career in chemical engineering not because they want to be a chemical engineer, but because they couldn't get an admission into computer science. It's a wrong way to start a career, right? It's a very negative way of starting the career. But it's a reality, And after you graduate, the pay packages that these two set of students get are so different, right? So, after 30 years, I would urge the young students who are making their choices, career choices, to ask what difference would I make? And I can tell them that if you become a chemical engineer, you'll be very happy to answer that question. You would say that indeed I tried to solve some of the largest, perhaps even existential problem for this planet because I was a chemical engineer. You can't put a value to that, to that I mean, it doesn't come as a paycheck in your bank, but it's a sense of satisfaction that you can't put a value on.
I think that sense of satisfaction keeps you healthy also. I think so. I think chemical engineering spans many value producing sectors in India. I mean, where India is a global leader. We talked of semiconductor, where India is not a global leader, but aspiring to become a semiconductor manufacturing house. And we need a whole army of chemical engineers, bright people, to really make the semiconductor ecosystem in India happen. There is another space where India is already a global leader, which is in the drug manufacturing space. And there is an army of chemical engineers that are already driving that ecosystem and will be required going into the future. Where do you see the pharma industry in India?
I think it's perhaps the most exciting sector today in India. Just to get you a sense of why it is exciting, I'll say two things. One, it is one of the few sectors in the country that has consciously invested in innovation. Easily about 3 to 4, 5% of their revenues are plowed back into R&D.
That's nearly at the global best.
Not many industry sectors in India do that, plowing back into innovation. Right? The second important exciting part about pharma sector is that it has made a big impact across the world. India is recognized today as the pharmacy of the world. About 22% of the generic drugs sold in the US, about 24% that are sold in the UK, and similar numbers in the EU have been manufactured in India. The active pharmaceutical ingredients, the APIs, have been manufactured in India. So we have made a difference globally, and if certain countries suddenly raise trade barriers, they will be impacted adversely.
And they've consciously left pharma out of all trade barriers.
So therefore, it's a sector where, like IT sector, where India is known to have made a big difference, pharma is another such sector to have made a huge difference to the world. The biggest example of that, the most recent one, is COVID days. If India had not stepped in to increase its manufacturing of vaccines, not just India, but several countries across the world would have suffered. It's we who supplied millions of doses of vaccine to the world, right? So it's a phenomenal sector, and you cannot have a pharma sector without chemical engineers. Let's be honest about it. You need fabulous chemists, and you need exceptional chemical engineers who together have built what pharma sector to India is today, right? And this is a sector that is growing, is even today highly aspirational, and they want to maintain their pole position in the world. They do not want to lose that leadership. It spans a whole range from very large companies, 75,000 crore companies, the Sun Pharmas and the Dr. Reddy's lab, kind of very large companies, to small MSMEs, 1,000 crore, 500 crore companies. So it spans the whole gamut of chemical industries, right? And they are all manufacturing not just the APIs, but also intermediates and so on, what we call key starting materials and intermediates. So it's a sector that is, it's very wide, employs a huge number of people. Many of these companies who have been set up, are now have a second rung of leadership. The founders, their second generation has now stepped in. Interestingly, many of these second generation company owners have been trained outside India in the best of the schools, or within India in the IITs and the UDCTs. So they have, their level of education as a chemical engineer or as a chemist has gone up. So they now are in charge of these industries, and they know that innovation is the key to maintain the leadership position, right? So one of the things that I experience, because at NCL we do a lot of work with these companies, right? And what I experience is these are hungry, young, next generation leaders who are taking over the reins of the existing pharma companies and creating new ones. And they're highly aspirational, right? They are highly educated, they're highly trained. They want to invest in innovation, right? They want to make sure that the next generation technologies come to India and we are early adopters of those technologies so that we maintain that pole position in the world. So it's very exciting. Normally, a tendency of complacency sets in. If you are a successful industry, you become complacent, and then before you know, the world overtakes you. But I don't see that happening in pharma. So I think I'm very, very positive about how the pharma sector is growing. To give you two examples of what I'm saying is thanks to maybe two things, maybe the advances in biology today, phenomenal advances in biology. What we could never anticipate doing 10 years ago, 15 years ago, we can do today. We can change the nucleotide sequences in genes at nucleotide levels. That's the kind of accuracy we have, the tools that we have with modern biology. And then you have the whole set of engineering techniques like fermentations, moving bed chromatographies, cross flow filtration devices, and so on. New unit operations that chemical engineers have built. So imagine this merging of very high tech biology and high tech biomanufacturing that is coming together, right? So that's one factor. The other factor is things like COVID. You could not have overcome that pandemic if you did not have access to vaccines, right? And what are vaccines? They are biotherapeutics, right? They're proteins, they are monoclonal antibodies, they're not small molecule drugs. They are bio-macromolecular drugs, right? Or oligomeric drugs, short chain, long chain drugs. They're very different than the typical small molecule drugs that we are used to. So a whole range of new drugs are coming, which were very bio-focused, right? So you have this biology, biomanufacturing from a science and technology point that has grown, and you have the need for such biotherapeutics that has come up, and come up very prominently because of pandemic, for example, or many rare diseases, genetic diseases cannot be cured without these biotherapeutics. These two, imagine two drivers which are coming together at the right time, right? On the one hand, you have science and technology evolved. On the other hand, you have the need from the marketplace. The societal need has evolved to want those kinds of drugs. And the pharma industry is right there. And so they are all moving now from small molecule drugs to biotherapeutics, right? And they want India to maintain the leadership position even in that field, right? You add another dimension of digitalization to it, right? For example, uh, how do I discover a new drug molecule? I have a disease. I sort of understand how if how I could prevent that growth of that disease, right? Spread of that disease from a biology point of view. There may be a receptor on a gene. If I were to sort of trap that or cover up that receptor, then the disease will not spread. So I know the mechanisms of how the disease would grow. What I now want to know is a drug molecule that can attach to that receptor. How do I decide that? How do I design that molecule? There could be any number. It's like a I can draw a chemical entity, but I don't know whether it will function, right? So it's a reverse problem. I know that I need to do this, but I don't know how to do it. I don't know how to design a molecule to do it. Now imagine if you go to a lab and say, I will synthesize 1,000 chemicals that I think might work, purely based on experience or intuition, right? And I go to a chemistry lab and I start, synthesizing milligram levels of huge number of molecules. And these are not easy synthesis. They could be 4-step, 5-step, 8-step synthesis. So to make that one 10 milligram of molecule, I need to make so many because there are 5-6 steps synthesis, right? So it's an arduous, time consuming, expensive process. And we may not have the time to wait for all this discovery to happen. But imagine you have an AI engine that scans millions of papers, learns from what has been done, and has the intelligence to say, you don't need to try 100 things. Maybe you should try just these 3 things. And that has a great possibility, a good probability that it will work, right? That is how drug discovery is happening today. So you have brought this new dimension of AI ML into pharmaceutical industry, which has suddenly crunched the time for drug discovery. I think I'm oversimplifying this, but I just want to make a point.
But I think this is already becoming a reality. You're not talking of a pipe dream.
It is a reality today, but not many industries are doing it today. There's still a lot more that this can be done. Now, this becomes even more complex when you have a biomolecule, because a biomolecule not only is complicated in terms of all the functional groups on a long chain of biological molecule, but how it orients in 3D space, what is its conformational possibilities, and whether that conformation is good enough to attach to a receptor of a gene. So added dimension of complexity, right? So all of this, biomanufacturing, systems biology, AI/ML, all of this coming together, a whole new direction to pharmaceutical industries is coming up. And I think again, chemical engineers are absolutely best placed to be part of this revolution and to make big impact. So there's another thing in the pharmaceutical industry that I think exciting that is happening is a lot of these chemicals today, even the small molecule chemicals, are made by what we chemical engineers call as batch processes, right? A batch process is like, honestly, is like cooking. What do we do in cooking? We take a vessel, we put it on the stove, we put stuff in it, we wait for it to cook and hope that what we have put in it and the time of cooking and the way we cook, the flame we provide, the heat intensity we provide actually comes out as a good eatable product, right? That is the hope. Right? Batch reactions are like that. You have a reactor, which is a vessel. You throw in all your raw materials in it. You heat it, or you may want to cool it. You wait for a certain time, what we call batch time. And a lot of things happen inside the batch, right? A lot of reactions happen. It's never a simple reaction like, A raw material going to B products. It is A plus B plus C giving C plus D plus E, and then B going to C, D going to E, A plus B going to this. It's a network of reactions that are happening in that vessel. Very much like what happens in cooking, honestly, right? And you hope at the end of the batch that what comes out is your desired product, which is the more, higher concentration product. And you have to live with everything else that you don't want is also there. And then you have to do all of these separations. You have to extract and purify the product that you want from everything that you don't want. So what is all happening here? You are waiting for a very long period of time. You are providing a lot of heat, or you are removing a lot of heat. You are stirring the pot, so you are consuming some power. And then you do a whole lot of purification steps. It could be distillation, it could be crystallization, it could be extraction. At the end of it, you get what you want, but you also get a whole lot of things that you don't want. Yeah. And that is what is causing effluent problems and so on, right? It could be gaseous emissions, or it could be liquid effluents, which then you have to spend a lot of time and effort and money to clean up that effluent before you can dump it into groundwater or sea. You have to clean it up, right? So it doesn't sound like the right thing to do, isn't it? What if you have a reactor where it's a small reactor where you can produce more, you don't have to heat or cool it too much. Uh, what you want only comes out, and very little of what you don't want forms, right? So your downstream purification is very simplified, right? That sounds like a utopian dream, right? But no, that transformation is happening, what we call batch to continuous. Your reactors don't look like a vessel, they are actually pipes, and they are very innovative pipes. So you are doing reactions in a pipe, okay, but very innovatively designed. You may be doing reaction in a ball mill. Ball mill is not a reactor, we think of it as a grinding machine, but you can do reactions in a ball mill. You can do reactions in an idli batter machine. We have done reactions like that. So what didn't look like a reactor, a conventional reactor, have started playing the role of a reactor, right? And this whole transformation of batch to continuous processes are happening today. And again, I sense that in the Indian pharmaceutical industry, they want to quickly adopt these new and emerging technologies, right? And the driver for that, honestly, is sustainability. It's a huge driver today in chemical industry, right? Chemical industry wants to become more sustainable, and sustainable is a word that is has many meanings. It doesn't only mean reducing carbon footprint or reducing effluents. Of course, sustainability means that, but it also means sustainability of profit. You know, so it's the sustainability of both profit and planet. I would say, right? So this is a huge driver today for chemical industry.
That's a very nice way to summarize. I think chemical engineering is all about sustainability of profit and planet. Um, Clearly, we've talked of three sectors: semiconductors, we cannot grow semiconductors in India, an ecosystem in India, without an army of good chemical engineers. We cannot maintain our pole position in pharmacy. We are already the pharmacy to the world, but we want to be the new drug discovery lab of the world as well, especially with biomolecules that presents a new opportunity, and that's a great space for our young men and women to step in and make a big difference for the whole world. Let's go back and talk about something that you are very familiar about, and one of the world's largest industries, oil and gas. And let's talk of the transformation that is happening in oil and gas, especially with green hydrogen. You alluded to it earlier. What new careers are you seeing sort of emerge in this old space of oil and gas? And why should a young chemical engineer today be excited about that space?
Yeah. So, oil and gas is a huge sector. Among the chemicals industry today, it is clearly the most dominant industry in terms of volumes, in terms of revenues, in terms of employment. It is the largest sector, right? And always been like that, and will continue to be like that for a long time. Uh, and this sector is therefore the one that also pollutes the most. The carbon footprint of oil and gas sector is pretty high.
You're talking the carbon footprint of the production of, let's say, gasoline.
End to end.
End to end.
Okay. So extraction of crude oil, for example,
Sure.
or extraction of
But we're
natural
not
gas.
talking, just to be clear, the carbon footprint of that gasoline being burnt in an auto.
No, I would say just the manufacturing part,
Okay.
right? So extraction of, say, natural gas or crude oil, right, starts from there. It is amazing to see how much natural gas is flared or leaks in the extraction technologies, right? And this is one of the big concerns today. How do we reduce the leakage of methane when we extract methane out from the Earth's crust? Because, as you know, methane is almost 30 times as potent a greenhouse gas as CO2 is, right? And therefore, minimizing methane leakage is very key. But it's happening today, right? If you come to refining industry, it's a huge amount of heat that is required to do the fractional distillation that happens in refining. You take crude oil and you distill many components out of it. You distill aviation fuels, you distill diesel, kerosene, you distill the what we call alkanes, the ethane, propane, then you distill the benzenes, xylene, toluene, and then you convert many of these chemicals, right? The ethane, propane, for example, the alkanes are converted into olefins, ethylenes and propylenes, and they then are the basic feedstock for making the polyethylenes and polypropylenes, right? So all of these are operations where a huge amount of heat is required. Each refinery, for example, would have a captive power plant, and gigawatt scale captive power plants, right? So what do you do there? You burn coal, you burn pet coke, things like that, which would create the steam that is required for the refineries, which would create the electricity that would required to run a compressor or a pump, right? So it's an energy intensive process, and with that energy that is spent, you are causing a lot of emissions, right? So refineries are today, given the volumes of crude oil or gas they process and the volume of excellent materials that they make, whether it is the fuel that you and I use in our cars or it is the plastic that we use in our homes, it all comes out of the refining petrochemicals, right? So they make excellent products and millions of tons of them, but in this process there is a lot of emissions that come out. So one of the key drivers in the oil and gas sector today is how do I reduce the emissions and how do I improve the efficiencies of all my unit operations, right? Because if I improve efficiencies, uh, then I will automatically reduce emissions. If I need less energy to make the same amount of products that I want by making my processes more efficient, then I'm reducing the emissions, right? And this is, I think, one of the most important drivers for oil and gas sector today. It's a low hanging fruit to make everything highly um, energy efficient. How do we do this?
This is not just Indian oil and gas trying to catch up to some global benchmark. We're already probably among the world's best in terms of efficiency and collectively pushing that global benchmark of it.
Absolutely, absolutely. The Reliance Jamnagar refinery, for example, is the largest greenfield refinery in the world, and it is a very complex refinery. There's a index of complexity of refineries, right? And it's one of the highest complexity index. The steam circuit in a refinery like that, they call it a steam circuit. How you valorize steam and minimize the use of steam in all these integrated complex refining processes that happen is an engineering by itself. In fact, there is steam engineering, right? So improving the efficiency of all your operations in an oil and gas sector, in a refining and petrochemical sector, is a low hanging fruit and one of the key innovations that are happening. And recently I came across innovation that is probably first to the world from India in terms of improving efficiencies of refining operations, and that is a fascinating use of AI/ML to improve the real-time efficiency improvement of a refinery. Just to give you a very simple example, I cannot divulge everything, but imagine that you have a gas compressor, okay, and an expensive gas compressor. Expensive because it is compressing combustible and explosive gases, such as, for example, a syngas, mixture of CO, carbon monoxide, and hydrogen, which we call syngas. You have a huge compressor that is pumping, circulating syngas, and thousands of tons of it on an hourly basis. So it's a mammoth machine. You have to operate it safely. And you can imagine that you don't want any downtime on this. You don't want the compressor to shut down, right? Because then switching to another compressor and all that becomes expensive and unsafe, right? So if you have an AI machine back in the background working and figuring out how this compressor is performing today, a second before or a minute before, what is its historical operating efficiency, and are there indications, early indications of something going wrong, right? Early indication. So this machine has learned over experience, by experience, looking at hundreds of thousands of hours of operations of this compressor, and when it failed, and what caused the failure. So it has learned, and now it is sophisticated enough to say that I can detect very early if something is going wrong with it, okay, and give an early signal, change this so that it doesn't get into a mode where you will have to shut it down, right? Imagine that, and that savings in downtime of a compressor has so much implications, both in terms of improving efficiency of the plant, reducing downtime, increasing operation maintenance charges, all of those. So it affects emissions, planet, and it affects profitability.
Very nice.
So this is one of the things of improving efficiencies in the plant. The second big change in oil and gas sector, and a little more downstream, that is on the petrochemical, refining petrochemical side, is what we call O2C, or some people call it C2C. So crude to chemicals, C2C, or oil to chemicals. What does that mean? If you take a barrel of crude oil, about 60%, 70% of it today, that crude oil is converted into fuels. The aviation fuel, the diesel, the petrol that we use, or the furnace oils that we use. So it is eventually burnt, right? You convert crude oil into fuels and then you burn it, like we burn it in our cars or buses that we drive. 30% or 40% is converted into chemicals. It could be chemicals that are used to make drugs. It could be chemicals that are used to make materials like polyethylenes and polypropylenes. Today what is happening is, as more and more renewable energy comes in and more electric vehicles come in, things are moving more towards electrons as much as possible, driving things using electrons. Motors which are electricity driven, compressors electricity driven, reactors which are today heated by electricity rather than by hot oil or steam, cars and vehicles which are driven by electricity rather than fuels. So as the world moves from using chemical fuels to electricity, and particularly renewable electricity, the demand for chemical fuels is expected to drop down, and it's already happening. So what do you do with that crude oil? You start to move it more and more to chemicals and materials. It is also a good way from an environmental perspective, because all the carbon in the crude oil is trapped into materials, and materials have a much longer lifetime. So you're sort of trapping the carbon and not releasing it back to the environment very quickly.
Sure.
In a fuel, that's what happens, right? You convert that carbon from crude oil into fuel and then you burn the fuel. So you're releasing the carbon back into environment. But if you are to convert that carbon into a material, the material stays with you for 15, 20 years. So the carbon is trapped in that material for 15, 20 years. You don't release the carbon back, immediately. So therefore, oil to chemicals or crude to chemicals is again driven by sustainability, the agenda for sustainability, right? And that is a big change in the refining petrochemical plants today. I have all my assets today on the ground, whether it's a fractional distillation column or a FCC cracker or a steam cracker or a hydro cracker. I have all these assets on the ground today. How do I use these assets now in a different way? Instead of making more fuel, I want to now make more materials, right? How do I do that, right? And that's a big driver today that's how the oil and gas sector is moving. The third is greening, and I already touched upon it, that instead of using oils and steam to heat things, you use electricity to heat steam. So today, for example, there's a big unit operation called steam methane reformer. So basically you take steam and you react it with methane in a catalytic bed, in a catalytic reactor. So water, steam reacting with methane to produce syngas, carbon monoxide and hydrogen, which is a fantastic fuel to do many materials, to make many materials. Right? It's a endothermic process, which means you have to provide heat to make this reaction happen. Today you use a lot of steam, you burn coal to make steam, and that steam is used to, or you burn methane to provide the heat. Mostly you burn methane to provide the heat for steam methane reaction. Right? 40% of the energy that goes in the steam methane reforming is converted into emissions, because you need to supply that energy. You need to burn the fuel like methane itself to provide the energy for methane reaction with steam. Now, instead of burning methane to provide that heat, if you were to use solar energy to heat the steam methane reformer by using electricity, so but it's a renewable electricity coming from solar, then again your sustainability agenda is catered to. You are reducing straight away 40% emissions. You are reducing, right? And heat transfer is more efficient, faster when you do electric heating than burning fuels. To just like electric motor is more efficient than a combustion motor, right? Similarly, it's the same principle here. Heating a steam methane reformer by electricity is more efficient than heating it by burning fuel. So this greening of oil and gas sector by any which way is a third important driver in this sector. So I think the whole oil and gas sector is at the cusp of transition, again driven mostly by the sustainability agenda, and some really exciting stuff happening in oil and gas sector.
Sustainability and the power of AI, predictive power of AI, seem to be making a big difference to a sort of a rather old sector in some sense. You've already talked of the digital transformation. I want to come back to that because AI is clearly on everybody's minds. And you said, we discussed this earlier, that if there is one core engineering field that is absolutely ripe and ready for the use of data science and AI, it is chemical engineering. And let's talk a little bit about what should a young man or woman do today, a student do today, to be ready for that strand of chemical engineering. That is probably a good intersection space to build a career in.
It is, and I think to every college that I go to or every university that I go to, and I'm sure it's the same in IIT Madras as well, you ask a young graduate chemical engineer, what do you want to do, and he or she will say, I want to be a data scientist, right? And I want more courses in data science in my chemical engineering curriculum, because they see that as a job opportunity, right? But their perspective is only from getting a job. As they grow older, they will see that it has much more than just getting a job, right? So I think it's really important that chemical industry adopts. It's a little late bloomer in terms of adopting AI/ML, but it should adopt it very quickly, because the potential that it can bring to improving efficiencies of everything that we do or new discoveries that we do is phenomenal. So in my opinion, as a somebody who would teach chemical engineering, the foundations of chemical engineering, you cannot escape from it, right? You could possibly introduce a small elective in AI/ML, but never introduce that at the expense of foundational chemical engineering, right? So I would suggest that at a sort of more at a master's level, my views, at a master's level, is that we should probably reduce the coursework load at a master's level, right? Minimize the coursework load and introduce more hands-on learning by doing, that sort of, and also specialize it to certain industry sectors. So that is where I would say a master's in chemical engineering that has that trains students for application of AI ML in chemical industry, right? And that would be a very valuable intersection where you are training students to become data scientists and applying it to chemical industry.
It's a very, I don't know if such programs exist, and maybe listeners should take this back as a cue for where there is an opportunity to build a program.
Yeah, I think there is a hunger for chemical industry today to get specifically trained people. There are pros and cons of it. I mean, one can debate about it, because you are trying to curate a young chemical engineer into a very specific sector. Like I said, a young chemical engineer trained early on in his career to become already a data scientist, and therefore for that young person the career more or less is fixed. You're going to become a data scientist in a chemical industry field, right? Is that the right thing to do, or you should develop chemical engineers who are more broadly trained and then they can go into any industry? That is the earlier thought process, right? And we have all trained like that, and we have adapted as per the needs of the chemical industry. But I think today the world is moving at such fast space that you want to get into the thick of things right away, and you can learn later on, but you need to get in there right now. You don't have the time to wait and adapt and change and learn. You need to get in there right away. That's my experience of what the industry wants. They want to have trained people in very specific domains so that they can quickly get them on, and as they join, maybe they can diversify during their career, right? So for example, I get pharmaceutical industry saying, do you have a master's program where students are trained to make this batch to continuous transformation? Do you have a master's program where students are trained in biomanufacturing? Or do you have a master's program where you are training people in data science but for applications in chemical industry, right? So I think the appetite of industry, I sense, and I'm not making a judgment on this, but I sense is to little bit change our master's curriculum and make it a little more focused for a certain sector, right? And then maybe as the students go in there and join and learn and make their way up the ladder in the industry, they will diversify, and some may get into more innovation, some may get into more finance and marketing and strategy and so on, but that's up to them to build their career within the industry. The industry wants early skilled trained people. I don't think you should do that at the bachelor's level, and I'm saying this because I sense a lot of kids who want to pursue bachelor's to become data scientists. But I say to them, don't do it at the expense of core chemical engineering. You have to learn your core first, and then you can get specialized. So that specialization can come in masters, not so much in the bachelor's.
I think what you're also suggesting is somebody who understands the core chemical engineering and has this added set of tools under their belt with data science and AI is far more valuable in the long run to the company. And even at IIT Madras, we now have a whole bouquet of niche master's programs that our students can upgrade into and develop that sort of fit expertise. We talked of several sectors. Beyond the traditional sectors, where do you see new chemical engineering opportunities emerge, possibly across the world and particularly in India, if you see any?
Yeah. So I would say again, going back to fundamentally, where is this new thing emerging from? What are the fundamental drivers for this new emergence of areas within the chemical industry domain? And it's sustainability. It's interfacing more with machines and biology, right? So adopting more of biology into chemical engineering, adopting more of machines. And when I say machines, it's Internet of Things, digitalization. I would say that these are three important foundational drivers. The fourth one, which is not sort of thought through, but the industry knows about it a lot more, is building resilience in supply chains. And it has a lot of geopolitical tune to it, right? Take the pharmaceutical industry today, right? We are great in making APIs. As we said, we are the global pharmacy. We export a lot of APIs, the active pharmaceutical ingredients to the world. How do we make them? We import a lot of key starting materials, KSM. We import a lot of KSMs, and then using multiple chemistry steps, which are complicated steps, we convert the KSMs into APIs, the key starting materials into APIs, which are the drug molecules. But we do import KSMs. So in the geopolitical system today, if there is somebody today a country today who says, I will not supply you these KSMs any longer, imagine the impact on the pharmaceutical industry. It's like in the Russia-Ukraine war, Russia turned off the gas pipelines and the whole of Europe suffered, right? So building resilience of supply chains is such an important factor today in today's geopolitics. And in the pharmaceutical sector, that is very important.
I think the overall picture of new and emerging sectors driven by sustainability agenda, by energy re-engineering, it could be green hydrogen, transition to green hydrogen, or as you said, the geopolitical balancing geopolitical constraints through supply chain resilience, all present new opportunities for the emerging army of chemical engineers. What apart from chemical engineering is a space, as you said, is not in the dirty plants. I mean, we've already discussed the fact that we are. These engineers really operate at a much higher level, at a much higher intellectual level as well. What are the soft skills and the business acumen required to really succeed in an industry job? I think we don't train our engineers well enough, and certainly not our chemical engineers too.
Yeah, I think this is one of the things that I learned when I worked in Reliance. We don't train our engineers to do very robust techno-economics, right? We expect that whatever scientific discoveries we make should be adopted by the industry straight away. And we often worry, why is it that industry is not interested in the science that we do, right? Let us be clear that industry works because it wants to make money. It's as plain simple as that, right? This is not, no industry works for charity. They want to make money, right? So if your science does not have the foundations of solid economics, it will not be easy to translate it. And why would an industry, take the science that you're doing and convert it into a technology if they don't see money in it? I don't think we teach our young engineers economics with the same rigor that we teach them foundational courses in chemical engineering. I think perhaps our professors, including myself, are not very adept at teaching a purely rigorous economics course or process economics course. I see that at IITs, for instance, you have a lot of professors of practice who are highly experienced engineers or professionals who have come from industry. After spending many years in industry, they have come to academics. I think they are the best placed people to teach this additional skill to our engineers. I think we should make full use of that resource that we have. We also don't teach our students too much of life cycle assessment. And as we talked, sustainability is one of the key drivers in chemical industry today. And how do you measure sustainability? It's another topic of discussion, really. But one of the metrics of sustainability is emissions, greenhouse gas emissions, or what we call carbon footprint in general. Do we train our students enough to really assess any given process for its sustainability? Quantify the sustainability of any given process, any given innovation. I don't think we train them with the same rigor as we train them in mass transport or reaction kinetics or so on. I think that is an absolute need of the hour today. So I think these two or three things, are very important for us to bring into our curriculum with the same emphasis as we do on the core courses. We don't give that much emphasis to them. There are softer skills, of course, how do you write, how do you communicate, articulate. I think the younger generation is very, very good at it compared to where at least I was. They're much more confident. They can stand on a stage and deliver a talk. Their communication skills are better. Language is no longer a barrier to them. So I think all of that is good. We can train it. We can hone those skills. But these 2-3 core skills, we don't train them enough. We should definitely incorporate in our curriculum.
You've been practicing chemical engineer for many decades, and you've seen changes happen along the way. We talked of many of those changes. What excites you most today that you think a young man or woman should absolutely be zeroed in on about the future of chemical engineering in India?
India as a country itself is emerging on the global platform today as one of the most exciting growth engines of global economy. I think let us be very clear about it, because that has ramifications across many sectors, including chemical sector. It's a sense of confidence that we have in the country today, right? We are not apologetic anymore when we face the world. We are very confident in saying, we are the global pharmacy, we are the global manufacturing world, we may be a leading steel manufacturer tomorrow in the world, we are already very big in IT services and so on. So there's a sense of great confidence in the country. And I think that rubs on the chemical industry as well. Okay. Innovation, for example. This whole sense of innovation ecosystem that has grown in the country. Today, I think we are the third largest innovation ecosystem in the world today, right? All this has come from this sense of confidence. Young engineers who want to take that risk, right? Which didn't exist when you and I were young students. Now this whole innovation ecosystem has really emerged. So now, for chemical industry, exciting parts are a huge amount of innovation supported by a robust innovation ecosystem has come up. All of that innovation is now aligned with sustainability development goals. They all want to look at greener everything, greener chemicals, improved energy efficiency, lower carbon footprint. Then whether it is green hydrogen or lithium ion batteries, it falls all under this sustainability index, right? And in all of these new innovation, new technologies that are emerging, there are no 100% mature technologies in the world out there. Now, why is this important? When India started its growth story, let's say in the chemical industry in the 1950s, we had nothing. We were not even manufacturing basic chemicals in this country, right? So forget innovation. We didn't even have the basic foundations. And therefore, we were always dependent on somebody else to give us technologies. And this whole mindset of licensing came from there. If I want to create an industry, there is no technology available within the country, So you go out, you pay money, you license, right? And you live with the fact that you will never get the cutting edge technology. They will only license to you the second generation, third generation lower generation technologies, right? So you live with it because you had no option. That has completely changed today. In the sustainability paradigm, let's say green hydrogen today, there is no one company in this world today who can claim, beating their chest, thumping on the chest, saying, I have the most mature green hydrogen technology. It's evolving everywhere in the world. Therefore, we are no longer catching up. We are right there. Okay, that is a significant change. And therefore, for an innovation ecosystem, we are trying to be among the globally best. We are trying to look at how can we make first to the world technologies, globally beating technologies, right? Uh, I think that's a big change. It's a change in the mindset of our innovators as well. I find that as one of the most exciting things. So, this sense of confidence, the fact that in the changing world, we are at par with everything else in the world. We are no longer one step or two step behind. We are with them. Uh, and then supported by things like digitalization, with a huge IT infrastructure, with so many data scientists coming along, we have that a huge resource with us, human resource. We have some physical resources. We are blessed with solar irradiation, so solar energy. We have 7,500 kilometers of coastline. That's a huge resource for us. So we are now looking at what are our strengths. So combine the strength with confidence and with the emergence of this innovation ecosystem. I think these are the most interesting drivers for chemical industry tomorrow.
Very nicely put. I think our biggest strength today is the people, the young men and women who are absolutely driven by innovation.
And highly trained people.
And highly trained.
Yeah.
Last point, we should talk about startups. We should talk about what sort of new ideas can be tested in the startup world. And more importantly, what should be the mindset of a chemical engineer wanting to start up? It's a different kind of a startup. And if you can also talk to how organizations like NCL or maybe the IITs can help.
I think it's a very, very important point to end this conversation because, we are producing a large number of good chemical engineers today. And, are there enough jobs available for them? It's a worry that as we started this conversation, I said that this was one of the worries of young engineers who want to pursue chemical engineering. So circling back to that point, are there enough jobs in the market today for chemical engineers, right? In the academics, there are only so many jobs available. There's only so many universities, and as professors retire, new recruitments happen. We've had a growth phase of universities. Many universities, new colleges, new institutions came up, but now we are, I think, plateauing out. Right? I won't see another big wave of huge number of IITs or huge number of ICERs or other universities coming up. It's sort of plateauing out now. So that means the job market there will also start plateauing out. In industry, yes, there is a growth. There will be requirement for chemical engineers to be absorbed. The more trained, the more skilled, specifically skilled, the better the opportunities for them. But perhaps we are producing more engineers than what is the absorption capacity for them, right? And perhaps young engineers also don't want to go in a job where they get a monthly salary. They are more ambitious, right? And they want to chart their own path. So they want to be entrepreneurs, right? India always had an entrepreneurial mindset. We are by nature very entrepreneurial, and therefore this whole career choice as an entrepreneur is a very fast growing career choice, and that's why we are the third largest startup ecosystem in the world today. And for chemical engineers, it's a great opportunity. Like I said, in the sustainability paradigm, there really aren't mature technologies anywhere in the world. When I say mature, it is TRL 9 technologies or MRL 5 technologies, manufacturing readiness level or technology readiness level very high. Those are not available today, which means there is enough scope for entrepreneurs to come in and develop better than the best, right? Uh, and that for chemical engineers is a great career choice today. What can we do as IITs or as NCLs in this country? Uh, we all have now good incubators. We almost all of us have excellent incubators, and we have good people who manage the incubators, very learned people, experienced people who manage incubators, who know the pains and the travels of starting from a young student to becoming a successful entrepreneur. That journey, what difficulties are there, could be there in the journey, and how do you mentor them, how do you handhold them. The incubators, many of them are doing a great job in that journey. What I would say is needed, I would say about two things are needed. We still don't have venture capitalists who are willing to take bigger risks, okay, who are willing to put in patient capital. Our startup ecosystem sort of accelerated because of IT. It is far easier to create apps, startups based on apps. You don't need much capital. You need only intellectual capital. You don't need hard assets on the ground, and you can make quick bucks, right? You can show your shareholders quick revenues and returns, great IRRs, and so the whole startup ecosystem accelerated in India because of that. Now we are coming to deep tech. We are coming to the hard problems, right? And that is where huge capital is required to be invested. Patient capital is required. These successes don't come in 2 years' time. They will come in 5, 7, 10 years' time. Do we have venture capitalists who are willing to put in money and patiently wait on that investment? I think we need more of that, right? The government will have to play a big role there as well. So that's the one thing we need. The second thing that is missing is what we call the valley of death. If I have a good science that I've done in the lab, I have translated that science into a fledgling technology at a low TRL level, maybe TRL 3, 4, right? For example, I have a proof of concept. I have used my scientific concept and proved that it actually works. From there to a commercial plant is a long journey, and it's fraught with risks. The technology at a lab scale can fail as you scale up. Hundreds of them fail. The money required to be invested in scaling up the technology is very high. The higher the scale you go to, the scale of operation, the exponentially higher amount of investment is required, right? So the risks are exponentially higher. And therefore, if you have a country that is very risk averse, they would not jump into it, right? And therefore, you have this valley of death where academics like us would stop at a technology readiness level, a TRL of about 4, 5, right? We are not set up to translate it all the way to commercial plant. Our systems are not set up to do that in an academic environment. The industry nowadays they all want ready-made technologies. You have to offer them on a platter, and then of course they will adopt it and put up commercial plants on it. But who will do this translation in between from labs to the commercial scale, right? I think in India there is a gap. In the Western world, there are a couple of good examples of how they have bridged the gap. In Germany, for example, the Fraunhofer chain of institutes is a fantastic institution that is created to bridge this valley of death. In the UK, there is a set of institutions called the Catapult Labs. In Australia, there are some other institutions, right? So we have to create now, in my opinion, new set of institutions with the specific purpose of helping this translation from lab to market and bridging this valley of death. And that is where such institutions can handhold innovators and startup young entrepreneurs, right? They will create facilities where new ideas by the entrepreneurs can be scaled up to commercial scales, right? Or faculties like you and me who develop technologies at a lower scale can go to such institutions and they will help to scale up and bridge that valley of death. So I think these couple of things are required in India. Um, we have everything else, in my opinion.
Fantastic. I think from where the technology is to where the people need to be, we've come a long way in this conversation. I think now is as exciting a time as any to make a difference to multiple sectors, pharma, oil and gas, the general landscape of energy production in India. I think it's as exciting a time as any to be a chemical engineer as ever. And thank you very much for coming on this
Thank you,
conversation.
Mahesh. It's been
Thank
a pleasure
you.
to be
I'll
with you.
close by saying no country can win a war without chemical engineers. Right? So that's also
I hope we don't have too many wars.
good. Thank you
Thank
very
you.
much again,
Thank you very
Ashish,
much.
for coming.
Thank you.
This has been a great conversation with Professor Ashish Lele, the director of National Chemical Laboratory and one of the foremost chemical engineers in India today. We are delighted that this conversation should be that we are able to bring this conversation to you and that it will be useful to all of you to help you make informed career decisions. This podcast is supported by IITM Global, an initiative of the Office of Global Engagement, a platform that takes India and IIT Madras to the world stage. Thank you all for listening. Until the next episode, be well, do good, and keep in touch. Goodbye.